We've learned about the concept of equilibrium in terms of solutions containing undissolved solute as well as vapor pressure in a closed system. Some chemical reactions, like the decomposition of dinitrogen tetroxide, are reversible, meaning that as the reactant forms product, the product also begins to form reactant. We have a chemical equilibrium occurring when both the forward and the reverse reaction are proceeding at the same rate. Once the system reaches equilibrium, the concentration of both the reactants and the products will remain constant. And so we would show a system that's at equilibrium by using the double arrow. When we look at the forward reaction, since we see that this is a unimolecular process, we could write the rate law as rate is equal to K of the forward reaction times the concentration of the reactant dinitrogen tetroxide. Remember that since it's unimolecular, we know that it's going to be a first order process to that reactant. Just as for the reverse reaction, since we have a bimolecular process for that reaction, we could write the rate law as rate is equal to the K for the reverse reaction times the concentration of the nitrogen dioxide squared. Since at equilibrium the rate of the forward reaction is equal to the rate of the reverse reaction, we can write this expression like this. So as long as we don't change the temperature and change the value of K for the forward or the reverse reaction, the ratio of those constants is also going to be constant. And so we refer to that ratio of the constants as the equilibrium constant. The equilibrium constant tells us on which side equilibrium will lie. At equilibrium, will we have more reactants present or will we have more product? So for the generic equation, the equilibrium constant expression would be written as the concentration of the products raised to the power of their coefficients divided by the concentration of the reactants raised to the power of their coefficients. Now we've been referring to equilibrium constant in terms of concentration or molarity, but since if we're talking about gases rather than solutions, pressure is going to be proportional to concentration for gases that are in a closed system. And so we can write an equilibrium constant expression for gases by substituting the partial pressures for concentration. So what does the value of K mean? Well, from our expression, we wrote our expression as products over reactants. And so if we have products predominating at equilibrium, we're going to have a large value for K. So a K that is equal to more than 1 is going to favor production of products at equilibrium. If at equilibrium we have more reactants present than products, remember reactants are in the denominator for the expression, and so our value for K will be a small number. So a value of K that is less than 1 is going to favor the formation of reactants at equilibrium. And by the way, even though since these reactions are reversible, we're still going to consider whatever is on the left side of the equation as being reactants and whatever's on the right side as being as product. Equilibrium can be reached from either direction. It doesn't matter whether we start out with products or reactants. At equilibrium, we're going to have the same proportions of all three substances present. As you can see, the ratio of reactant to product from our expression, which is our value for K, is going to be the same as long as the temperature doesn't change, regardless of what concentrations we start out with. We can also convert between the K for concentration or molarity of solutions and the equilibrium constant for gases for pressure by using this equation, where delta N is the moles of gas on the product side minus the moles of gas on the reactant side. It's important to be able to look at the equilibrium constant in terms of what's happening with the equation. For example, for the forward reaction, our equilibrium expression is going to look like this, and the value of our equilibrium constant is going to be 0.212 at a given temperature. If we reverse the reaction, then our expression then changes accordingly, giving us an equilibrium constant that's going to be the reciprocal of that for the forward reaction. Doubling the coefficients in our original forward reaction then will cause our equilibrium constant then to end up being squared. And finally, if we have a reaction that's made up of a series of 2 or more steps, then the equilibrium constant for the net reaction would be determined by adding the equilibrium constants for each of the individual steps. When all of the species involved in a reversible reaction are in the same phase, say they're all gases, then they form a homogeneous equilibrium. But we can also have situations where the substances involved are in different phases, forming a heterogeneous equilibrium. Solids and pure liquids involved in heterogeneous equilibrium wouldn't be included in the equilibrium constant expression. The reason for this is that the concentration of a pure solid or a liquid has a constant value. If the mass of the solid, for example, were doubled, its volume would also double. So its concentration, which is going to be the ratio of its mass to volume, is going to stay the same. And because equilibrium constant expressions include only the terms for the species whose concentrations are actually going to change in a chemical reaction, the concentration of the pure solids and pure liquids are not included, even though their presence is necessary for the equilibrium to be reached. Here we'll work out a problem. We have an equilibrium being formed between hydrogen gas and solid iodide, forming hydrogen iodide gas. And we're given initial concentrations of both species that are allowed to come to equilibrium and are asked to calculate the equilibrium constant at a given temperature. So if we unpack the information that's given to us in the problem, we have a balanced equation, and we set up this ice chart. Our initial concentrations, what happens as they change, and where are we at equilibrium. So we're given starting concentrations for both the hydrogen and the iodide. Initially, we're considered to have no product, because we're saying initially before the actual reaction has started to proceed. We're also given a concentration of our product at equilibrium. And since we know that the stoichiometry of the reaction is 1 to 1 to 2, and we know that the product has increased by this amount, then we know that these concentrations have decreased by half that amount. And so subtracting, we get the values that we can plug into our equilibrium expression and solve for the equilibrium constant. And since our equilibrium constant is greater than 1, we know that at equilibrium we will have more product than reactant.